Today we are hosting Professor Georg Martius from University of Tübingen. He is a full professor at University of Tübingen and director of Autonomous Learning Lab at Max Planck Institute for Intelligent Systems in Tübingen. He did his postdoc at IST Australia and the postdoc at Max Planck Institute for Mathematics. He received his PhD at University of Göttingen. His research interests are internal model learning, reinforcement learning, control of robot body in development fashion, and intrinsic motivation, haptics, and representation learning. Today he's going to talk about machine learning for autonomously learning robots. Thank you for accepting the invitation. This stage is yours.
Yeah, thanks a lot for the kind introduction and for having me. I'm really happy to talk to you about my research on machine learning methods for autonomously learning robots. So my vision is that we have at some point versatile learning robots, because imagine if we had those and they can be trained to perform new tasks quickly and become dexterous in these tasks. They really would be valuable assistance to humans in several tasks, for instance, collaborative assembly tasks, in tackling global challenges like planting trees where people can hardly access areas, or taking care of elderly people. Or another topic that I'm quite interested in is whether we can transform the way we do agriculture with robots in a more biodiverse setting. For all of these applications, we really need learning, because it's very hard to pre-program these robots from the start to do what they need. So learning is needed from my perspective. And now the question is, how do we get there? And for this, I'm taking inspiration from developmental learning in humans, for instance, where we start as a baby, don't know a lot, can't do a lot of things, and then develop in a developmental process to a capable human being that is able to do a lot of things. And the question is also there, what are the general principles that are driving this progress? And a lot of disciplines have been looking at this under different names. One name would be intrinsic motivation. So this is somehow deciding what an agent should do if there is no particular external task at hand. And there is also another name for this is task agnostic learning. So what to do if there's no particular task. And here on the right, you see kind of a big list of different groups and topics. You don't have to read all of them, but we can group them into different aspects. For instance, we can group them into those which would try those intrinsic motivations that gain sensory motor coordination. There we have principles like information theory and dynamical systems-based intrinsic motivations, and I will talk about one of these methods today. Then the second part is those motivations that are directly geared towards gaining understanding, so mostly surprise-based methods or predictive information gain. I will also talk about two papers in this realm. Then there are intrinsic motivations that are there to gain control of the environment and to learn particular skills. So these are typically competence-based methods and hierarchical reinforcement learning. I will only touch on those shortly. And then there are these which we can say that are intrinsic motivations to visit particular states. So this could be empowerment as a prominent principle, or causally impactful states or regular situations. And I will also talk about this. Okay, so this is a little bit of an sort of overview of the different types of things that we've been looking at, among others. And yes, so I would like to jump in immediately in the first thing, which is let's say, very high level question. If you have a system, let's say like a little bit like a baby, and it has no idea what is it about, then you can ask generally what should be the sensory motor coordination of that system doing. And there are different extremes, right? One extreme would be the sensors are completely flat. There's nothing happening. It's kind of a dark room problem. It would not do anything. That can't be the solution to a developing system. The other option would be that you have a random sensor stream, which is also likely not to be good, because you are not doing any structured behavior whatsoever. And then the last one is where you have somehow both variety and predictability structure. So this is the kind of very generic question that, or like principle that we can already use and try to formulate this in some formal ways. And this is something that I've done many, many years ago. And we have been looking into dynamical systems theory, where we say that we don't want systems with trivial fixed points, and we want some kind of balanced dynamics. People also call this critical dynamics. In information theory, this can be phrased as the predictive information, namely the mutual information between the past and the future should be high. And so here, this is a video of something I did almost 12 years ago, where we had to still write our own simulators and so on. In this system here, all of these creatures have no idea about themselves. They have exactly the same kind of brain with this very simple intrinsic motivation to create sensor coordination based on this predictive information. And you see that, well, first of all, they're all moving. They look kind of lifelike. They are reactive. And so that for us was really interesting, in particular, as these kind of behaviors develop immediately, like sort of in this moment that you look at, there's no pre-training or anything involved. It's really a very simple process that can yield this very interesting exploration behavior. Of course, that didn't do anything specific. And we took this very general principle based on information theory and dynamical system theory, and then looked into more biologically plausible update rules, and took and developed the following method, which is called differentiable intrinsic plasticity, geared towards creating this coordinated behavior. So imagine you have this robotic system with an input X, which are sensor values, outputs Y with their actions, and you simply have a controller, which is one layer neural network that connects them. And you can now look into neuroscience, and there has been the idea to have Hebbian learning, which would connect input and output. So if input and output fires together, you create a synapse, strengthen the synapse. Then there was this idea of differential Hebbian learning, which means you change the synapse according to the change in the velocities of the input and output. So if input and output change together, you strengthen the synapse. So we have a very simple dynamics of each of these little synapses here, according to the change of X and Y minus some damping. And this alone would not create you any interesting behavior that is related to the outside world, because no sensor values, no reaction of your sensor values are somehow entering this. And so we came up with this idea to add an inverse model that takes the next sensor values X prime, propagates them back through the inverse model to some hypothetical Y. So that is with the interpretation, if I would have done this kind of action, I would have observed what I'm observing now. And then with this kind of new Y, new action, I'm now updating this synapse. So that's it. So it's a very simple thing. I observe the next state, project this back somehow into an action, and then I update my rule. So that's why we call this differential plasticity, and extrinsic, because we take the external world into account. So somehow now it works. Okay. And then we end up with this very simple dynamics, like 2 lines, this differential Hebbian, and also some normalization of the controller matrix. And so just that you see that this is really simple to implement in a way. It's really a one layer neural network and this weight normalization, and the inverse model is for us simply an identity matrix, because we think that every motor has sort of one sensor attached to it. So it's a very simple approach here. What it does, though, is a bit intricate, because first of all, this normalization makes sure that small changes, small sensor values are somehow amplified, and you will get some activation, and then it increases velocity correlations. So this controller matrix, because it somehow contains here this product of these velocities, it fosters those correlations which are already in the data, and it aims for some kind of self-consistency. And so it creates behavior that by itself, by its velocities, can recreate this controller structure. So that's kind of funny. So you do a little bit of behavior, and then this system will settle into some fixed point where it continues this behavior. And we have been applying this to, for instance, this robotic arm here, which has 9 muscles, and otherwise can move sort of freely. You see that we attach here an object, and the arm starts to shake. And if I come in and hold it, it immediately reacts on what I do. It also changes the directions if we are attaching the bottle in different directions. So it really has some kind of feeling of the embodiment. So this was all the stuff that we have been doing with this many years ago. But now let's go and see how we can use that for more modern robotics and stuff where we actually want to do something. So for this, I would like to go a little bit into see how complicated exploration is when we want to do learning. And we will see how we then use this kind of thing that I just explained to you in a moment. So this is a standard arm with two motors, and we can just apply a random noise, and you've seen that this was nicely moving and it would just explore all the space easily. Now, if we do the same thing, same random noise now on a system with muscles, so we have 6 muscles that are connected here into this arm, which is quite a prototypical version, then you see that the arm is hardly moving and we would not explore any of the space. On the contrary, if we now use exactly this embodied exploration, so this DEP rule that I explained to you, this would immediately create this kind of exploration as you see on the right. So it would create a large movements. It would essentially show us what the system can do. And as in maybe more interesting example, here on the left, you see the same with the ostrich with 121 muscles. And here on the right, you see the same with this embodied exploration. And you see, of course, the ostrich falls, but then it makes really interesting behaviors. Whereas on the left, it just essentially it doesn't move a lot. Okay, well, so far this is nice, but we haven't really seen any interesting behavior. So how do we translate this into something? Let me just maybe stop this video for a moment. Wait, this video should maybe, well, I can't stop this now. Anyway, you will see on the left already that the ostrich is now nicely running, really, really fast. Look at how the legs are extended here and how quick this is running. The neck is, of course, not part of the cost function, so it just locks it. But how did we get there? We interleave now this exploration with this intrinsic motivation, with this DEP, and the policy optimization as shown here on the right. So you have a little bit where our reinforcement learning policy is running. So we have an our deep reinforcement learning agent, which is maximum a posteriori policy optimization. I have this here on this slide. Actually, these slides should have been inverted, never mind. So, and then we have short snippets where this embodied exploration runs. Then we have again MPO running and so on. In this way, our DEP is able to create new movements, which are still kind of coordinated, and then MPO can take over and develop this into a proper walking or recover from some kind of perturbation. So then these behaviors become really robust. So on the right, you see what happens if you didn't do this optimization. You would just end up in a in some local minima where you're still running, but you're much slower and much less robust. So in the paper, we show how you can perturb the system and how much it's robust to these to perturbations, for instance, and energy efficiency and this kind of stuff. Now, recently, we have been able to also apply these methods to humanoid simulations. So this is high fidelity simulation of a humanoid with muscles here now, with different number of muscles. And you see that we get really nice walking behavior. Of course, the system doesn't have arms yet, so it can't be as natural as we would like. But what is really, really interesting is that we are managing to get these behaviors without any behavioral data. It's really just reward optimization, right? So we have very generic rewards, like we want forward velocity to be a certain value, and we want to avoid joint limits, and we want to minimize energy. That's it. That hasn't been done before. Before it was always with particular demonstration data. And now with this method that allows us to solve this really hard exploration problem and get to these really optimal behaviors, it really opens the door for now studying systems with, for instance, a patient where we would simulate some kind of lesion, or we would add some exoskeleton and other kind of stuff to this. So this is really exciting to us. And so this is a archive preprint so far. And here you see, I don't know, this is somehow doesn't really work too well, but you see part of this video. I can just move it in here, where we have now this system running on some funny ground. It hasn't been trained on this, it only trained on flat ground. And I just thought I share these funny videos with you. I'm not sure whether this comes through nicely through Zoom. I hope you can still see this skeleton running around here and enjoying the falls. Okay, so what have we been seeing? We have been seeing that we are able to create realistic movements in high-dimensional systems and create really adaptive behavior for this. So let me see whether I can now. Yes, this works. Good. Using these methods, we have been also part of the organization of this Mayo Challenge at Europe's 2023, where we are asked the community to study these systems, musculoskeletal systems, where we had grasping with a hand task and also some of these running tasks. And our method here, this DEPRL, was a baseline in this method to get people off the ground. So this was really successful. We had a lot of people participating, and the results are really, really cool. Now, so I already summarized this, but what is really interesting is that we are able to create now a nice behavior for high-dimensional systems because we are able to explore them well and really find a very good optima and not go into local optima. Still, of course, this takes millions of steps, but this is all in simulation, so this is all fine. Now, the second thing I want to talk about is a different kind of intrinsic motivation, namely one that tries to look at causal action influence. So try to understand whether an agent has particular influence on an environment or not. And this is maybe particularly important in context of manipulation. So if you look at the following setup, imagine you have a robotic system and like this arm, and it can move around and manipulate objects. If it is in this situation where it's far away from the object, it cannot really manipulate it. So it doesn't really have any influence on the object, whereas on the other side it has. And so in order to model this, we have been looking at causal influence, causal modeling. And classically, people would look at the global causal graph, namely the idea that whether there is in principle any kind of influence between or any kind of dependency between the variables. And so this would always be a fully connected graph where we have here the current state, and we would influence the next state, for instance, the robot and the object. But we have added now this local view where we are saying, okay, let's condition ourselves on a particular state S, and then ask in this particular state S, what can I influence in the next time step? And then we see that now suddenly the action is not influencing the object at the next time step. It's only able to influence the arm, right? So in a way, there is an arrow missing. And we would like to know when this arrow is missing because it's important for us, or in particular when this arrow is there, in order to know what to do. And we formalize this by a mutual information objective that measures the mutual information between the particular object, for instance, here this S2, and my action conditioned on a particular situation. And we can nicely compute this practically by writing this mutual information as a KL divergence, where we are taking a random policy and we are measuring the difference between what happens if I do particular action and what happens if I do, if I marginalize over the action. So what happens if I didn't know the action, the particular action? If there is no difference between the two, right, then my action doesn't have any influence, doesn't change the outcome distribution of this particular SJ here, which was, let's say, the object. So it's quite intuitive, right? If my action makes a difference to this distribution, a particular one, then I have influence, otherwise not. So in this way, I can measure it, and I have now a value, continuous value, that describes me how much influence I'm having. Now let's see how we can use this. A relatively simple method. We are running this with a probabilistic neural network that predicts these distributions, and then we can now use this. And the first thing we can do is we can just plug it in as an intrinsic reward, no task reward in this case, where we have here this fetch, pick, and place environment in GIM, as you probably know, kind of a common environment in deep reinforcement learning. And if we are just adding this, we can now look what happens. So for instance, the green line says object is moved. Yeah, that happens very quickly. And also object is lifted into the air. And this other line, you also see that our measure, the chi measure, is actually increased by the policy. And then we can do more interesting stuff. We can start to use it as an active exploration. So we can, for instance, say, let me choose the particular action. If I do a random action and not the action that is coming from a policy, when I do a random action, I'm choosing the action that has the maximum, that has this maximum causal action influence, right? I can go through each action and ask. And you see that this increases the performance of this task quite a lot. And also I can, so this means I have a task reward and I add this additional reward. And then I can also do it as an exploration bonus, where whenever I reach a state that had causal impact, I'm adding a little bit of a bonus. And depending on this value that I'm adding, I'm getting quite a bit of performance boost with respect to the baseline, which was the orange line. Now, what was even more powerful is to use these information for experience replay. So I have my episodes, and what often happens, I have episodes which are completely meaningless. Nothing happened in them. The robot just doesn't do anything with respect to the task. So it doesn't move the object, for instance. And then if I'm using this chi measure to decide whether an entire episode should be replayed or not, then I get from the baseline method to this purple method here, which is really quite a strong one. As a simple comparison, this is prioritized experience replay, which uses another method to prioritize episodes, and that is far less effective. We've been using the same kind of idea, this causal action influence, now also for data augmentation. And we're having a paper at the Europe's, we had a paper at the workshop for this, and hopefully it's coming out also at the conference soon. Cool.
So can
yes.
Is the idea to sample the episodes where the actions matter more?
Exactly. Exactly, if you have your replay buffer, you sample those episodes more often where you had causal influence.
Why would it help? Because otherwise nothing is happening kind of situation, or
exactly. In the other cases, you, for instance, would not even touch the object nicely, or you would have maybe it falls out a lot and so on. And so in this way, you kind of see more of the good data. It's still just a prioritization, right? You still see also the bad data, but this it seems that this experience replay is really quite important. It's really quite sensitive. It's really quite sensitive to the kind of data you're seeing. And as you do at the beginning, just random exploration, the data is actually quite bad.
I see. Okay, thank you.
Does it make sense, or?
Yes, it does. It's great, actually. Yeah.
Okay. Are there any other questions while we are anyway having a break for a moment? No. Okay, then I continue, but please don't be shy to ask questions. Cool. So now, well, I have been sort of in the title of the talk, there was also this term autonomous learning, and you may be wondering, okay, so far he has been telling about a few of these motivations, but how do we really get to this kind of vision that we have a robot that can sort of prepare itself for future tasks in some kind of task agnostic phase, which we call free play phase, where I can just let the robot do whatever it wants, like a kid playing around, and later I can come and ask to perform that it performs a particular task. And of course, we would like that these kind of methods would be so sample efficient that I can run them even on a real robot. Give me a moment. Okay. Of course, I mean, I've been talking already about reinforcement learning, but I haven't really told you of course, what it is, but I guess you know, it's this system where you are trying to find a policy that maximizes discounted future reward. So I'm doing something in the environment reacts, and so on. Since I don't know anything about the environment, this problem is really complicated. And I need to do trial and error learning, which is, of course, needs a lot of samples. It must be data. It cannot be very data efficient because I really don't put a lot of assumptions in. Mostly this is prohibitive for real world if I just do it in this plain way. An alternative is to use a model of the environment and then run my reinforcement learning against this model. Then suddenly I can, of course, spend lots of samples because the model is not so costly. I can do mental simulations. And also it allows me to do reward computation in imagination. So I can do something and then think, maybe this solves the task or not. But it also requires me to be able to compute rewards. Anyway, so this model now needs to be somehow aligned to the real world. So I need real experiments to ground this model. So this is what model-based reinforcement learning tries to do. This works well if I have an idea that my model, so this type of thing that I'm using here, can generalize well from the data that I've been seeing so far, better than just the data that I've been collecting so far. And so now with this machinery in place, we can think about, as we are able to compute the rewards ourselves on imagined states, we can look at our intrinsic motivations and see which of these are particularly suitable. And here I group them into two parts. The first part, what I would call retrospective or hard to predict stuff, hard to predict quantities. For instance, curiosity, learning progress, competence. These are typically methods that I can do, and then afterwards I can see, yeah, okay, I made some learning progress, or I managed to solve the task. So it's not that they cannot be predicted, but they are harder to predict. Prediction error, for instance, in this ICM module or novelty search. So this kind of stuff. So they are interesting, but they are hard to predict. So the other parts here, namely predicted information gain, reduction in epistemic uncertainty, empowerment, causal action influence, these kind of things, they are easy to predict because, I mean, as I will explain in a moment, you can compute them on a predicted state, on a state that you have not seen in the reality. And that's really interesting because now suddenly we can start to use our model, plan for those, and not have to do them first to see whether they are good. And so you will see why this is really making quite a bit of a difference. Okay, so this predicted information sequence can be used in model-based optimization, and they are nicely predictable. Okay, and then I want to show you two kinds of instantiations of model-based RL, I would say, that have been looked at in the literature. One is where we do planning at learning time. So we have our model, and we use that model to collect data nearby real observations. So imagine the black line is the stuff that I've been doing, and the green line is maybe the optimal behavior, just in this cartoon picture. And then with the model, I would roll out sort of every of these states, I would roll out alternative futures, and I would have this data as part of my process, of my learning process. This solves a particular task and is able to solve this global optimization problem, so quite powerful. Instantiations are MBPO, model-based policy optimization, or Dreamer, for instance. Then the other version is planning at runtime. That's a bit more close to what, say, classical robotics would do, namely to do a planning method that would take the model to plan in the immediate future what to do best. So here, again, in this similar picture, I'm here at the start, and then I'm planning what needs to be done in order to get closer to this, to my, let's say, green line, for instance. And what I can do with this method, I can now plan for a new task on the fly. Whenever I change this task, I just can plan for that new task immediately. But I can only plan for finite horizon problems because that's it, right? This is a complicated optimization problem. I cannot solve this for a really long problem. So quite different. The top one allows me to solve a task to perfection, a particular one, and the bottom one allows me to be very flexible in a new task, but I have to go for short horizon plan. Models of this kind is the PETS paper or Plan to Explore. So this paper was called Reinforcement Learning in a Handful of Trials. And now I will actually talk about the second part because we see that this is really quite powerful when we combine this with these intrinsic motivations. So what do we need to get these models, these systems to work well is we need a fast optimizer and we need a good word model, right? Both are kind of problems. And we have been solving these problems in the past. So the first thing I want to talk about is the planning part. If we have model-based planning, we have now the task to find an action sequence which solves a particular cost function or the optimized vertical cost function on the fly. And although very primitive, these sampling-based methods have been quite popular. For instance, cross-entropy method. It's not the cross-entropy cost function that you maybe use in deep learning. It's a different method. It's a sampling-based zero-order optimization method with this name. And what does it do? Here, look at this picture. Let's say our agent is here, and it, let's say, wants to go to the goal. And you sample action sequences from a Gaussian distribution with a particular mean and variance. Then you sample them, and then you evaluate them, see which ones are good. So here the green ones are the ones that are better than the other ones. So let's take those, refit the parameters of this distribution. So you get a new Gaussian for the actions and you sample again. And then you already get maybe a little bit better trajectories. And after a few iterations, you are maybe happy and take this yellow trajectory. And then in robotics, typically you do model predictive control, means you execute one action and then replan. Okay, so that's fine, but this is not really optimized for the kind of robotic type of setups that we want, and it's not really optimized for this MPC. So we went and optimized this, which we call improved cross-entropy method, by adding some memory of the previous optimization runs, and in particular added a different type of noise to the exploration. So not white noise, so independent Gaussians that are for the actions, but we add a temporal correlation. In physics, this is known as colored noise, and it's technically noise where the power spectral density, so how much my which energy is in every frequency band of that noise, is distributed according to such a power law, 1 over f to the beta. And so now let's look at our cartoon picture. It means that we are likely, when we do one action, we are also doing an action which has a very similar direction. This is sort of this temporal correlation doing. So we see that after a few iterations already, we will have much more smoother, much more far-reaching exploration trajectories. And so then we will able to solve the task nicely. Okay, let's see. This is our cartoon picture. Let's see whether that really works. So here on this slide, you see on the right, you see, first of all, the behavior. The system is planning for very few samples. I will explain what that means, and is able to open that door easily with this hand, which has quite a few degrees of freedom. It can move, but it also has the fingers, so it has like 20 degrees of freedom-ish. On the left, you see the actual qualitative results. So quantitative results, sorry. So on the x-axis, you get the budget. Budget means how many of these samples are you able to, so these trajectories are you able to plan into the future every time step. Y-axis, you see how good you open the door. And so the baselines are the standard CM method and some CM that they used in this particular paper where they did some hacks, and our method here. And you see that, of course, we are much better, and we are actually really, really strong in this. So what does it mean here? We are able to solve this kind of task with just 45 of these trajectory samples per time step. And that works because we have this color noise. So we have smooth trajectories, and we are also using previous partial plans to continue. So even if you're not finding a solution in the first moment, we are finding it maybe after 10 or 15 time steps, which is just a fraction of a second. This is all here with perfect models. So we are not actually learning a model, but we are using the simulator, the ground truth model. So that's a bit cheating, but this is only to check whether this planner is really good.
You have a question?
Yes, absolutely.
How do you implement the memory? Do you keep the sample trajectory somewhere and compute similarity? How do you implement the memory?
No, it's actually very, very simple. Let me go back. Imagine you have been planning this down here, right? This trajectory. And then you execute the first action. So let's say the first action brings you here. And then the rest of this plan, this part, of course, is still probably a good start, a good way to start from, right? So you warm start your planning for the next time step with the rest of this trajectory, first of all. And then you also are keeping, let's say, maybe the best. So you're always keeping this distribution around, but you also maybe want to keep a particular sequence around that is the best. So there are a few of these tricks, but there's no heavy compute or no similarity measure. It's really just that you take, essentially you warm start your optimization. If you did one action in the real world, you warm start your simulation, your optimization in the next time step to continue the plan that you have been developing and adding some random sample at the end.
I see. Then the initial samples matter a lot, right? Like if you don't have good initial samples, then you can never recover from that, right?
In a way, yes. So what happens often is at the beginning, you're maybe not seeing any samples. So then this distribution is not really specific. So you will kind of stay and do nothing because you have random end actions. And then you optimize, and at some, like over the steps, and at some point you will see maybe a trajectory that sort of hits the target, and then you start to funnel in. Funny enough, these methods often work better if you have sparse rewards rather than if you have potentially wrong continuous rewards. So if you have rewards that bring you to the goal, but maybe there is some obstacle in between and they misguide you, then maybe your optimizer gets stuck very early on to this kind of method. Whereas if you had sparse rewards, it really needs to find the solution. Maybe it gets a little bit slower because at the beginning it can't solve it, but then after sometimes it solves it. So this is some of the experiences we made. You really need to make sure that these methods do not do premature convergence to the first best plan they found.
I see. Okay, thank you.
So here is a bit more that you see that it's not just this one door opening task. So we have half cheetah running, we have humanoid stand up, which is really quite challenging. So the humanoid is laying on the ground, it has to stand up. Typically methods converge to these kind of just sitting position. And here you see that we are able to speed this up by several orders of magnitude. That's the log scale here on the x-axis. So that was really cool. This was our sort of enabling method to make this planning stuff work. Now, let's come to these models. Let's just, use a model. What can go wrong? Well, lots of stuff goes wrong. One of the real problems is that I'm now optimizing against a learned model, and my optimizer tries to get the best performance, and it will just find any kind of loophole that this model has. Anything that the model thinks it can achieve, but it's not correct, it will exploit. Another example, of course, is if there's something in your environment that you haven't seen yet, you don't know, right? For instance, let's say this is blue shaded area is the area that you have been already exploring. Then there is maybe some obstacle in the way, and you would want to go to this direction. You would just plan to go through that obstacle, obviously, and the model will not know about it. So what do we need to do? We need to somehow know when the model doesn't know. And so for that, we need to have models that have a notion of epistemic uncertainty. So very short introduction to this topic. So there are at least two types of uncertainties that we distinguish. One is called aleatoric, and the other one epistemic. Aleatoric uncertainty is the one that is inherent to the problem. It's kind of noise, and it's irreducible. So imagine you get data in this region here, and then the aleatoric uncertainty is this uncertainty here that is sort of the spread of that data within the data distribution. The epistemic uncertainty, on the other hand, is the uncertainty which is outside of the data distribution. So because of lack of data, you don't know what is actually happening here. And so why is it interesting to distinguish them? Well, aleatoric uncertainty is something you probably want to avoid. So if something is just inherently uncontrollable. Whereas epistemic uncertainty, you want to seek if you want to explore, but if you want to do safe exploration, you want to also avoid it. Okay, so it's important that we are able to distinguish them. And we do this practically with a relatively simple method, namely ensemble of probabilistic deep nets. So why does that work? So I have here, I show you the prediction of 3 of these ensemble members. So each of them predicts a Gaussian. And on the data, these methods will likely coincide because you've been trained on the data. So essentially, the average of them will give me a good estimate of what's going to happen. Although outside, I see that they will be likely diverging in their predictions because they haven't been trained on, and they haven't seen any data, and they had different initial conditions. So it's the typical ensemble argument. And now we are able to express here the sort of deviation between the ensemble members as how much we are uncertain, how much we don't know, which we call epistemic uncertainty. Okay. Then to use this in n-step predictions is a bit non-trivial because your uncertainties get mangled up if you do n-step predictions. But we have a paper that solves this. This is this second paper here on this list. So this is the original paper. Sorry, what happened? This is the original paper, the PETS paper. Then the Rather paper does this entanglement of these two types of uncertainties. And then we also have a method that is also quite instrumental to learn probabilistic deep networks, that we have a fix to the negative log likelihood loss function, which really makes otherwise these networks very, very challenging or impossible to train sometimes. So if you want to train anything with negative log likelihood, check out that paper. The fix to the problem is super easy, and it was really quite a game changer for us. So now let's look at this intrinsic motivations again. We can now suddenly use these predicted ones, these predictable ones, to actually plan, and that's exactly what we're going to do next. We are going to plan for this predicted information gain, or essentially a proxy, which is the epistemic uncertainty. And later on, we'll also look at some other method like a regularity method. So now let's do this. So what is really interesting in this planning method, that we are able to change our target every time. So let's say we make a step, and then next time step, we can already change the target because maybe our original thing is not interesting anymore because we have already collected data. So we are really able to plan this on the fly. And so we are very flexible, and we can plan many, many steps ahead for potential interestingness or potential positions where we have uncertainty. In model-free RL, on the other hand, we would need to first sort of observe it, then collect reward, and then we would slowly update our policy. And by the time the policy figured out how to do it, probably this kind of behavior is already not interesting anymore because I have seen it. So for this kind of quick exploration, I believe that this planning is really a very interesting method to do. Okay, so let's look at our concrete implementation. So we want to collect essentially like active learning. We really want to collect data, which is very helpful for the agent to patch its model to understand how the world works. So what we do is we plan for many steps in the future to directly go to the unknown. So we are planning to be surprised. Again, we used exactly this ensemble methods, as I mentioned before. One maybe could also use Bayesian neural networks, but these ensemble models are working very well in practice at the moment. And here comes our concrete setup that I would like to show you. Namely, we have our pick and place robot, so the robot with several cubes. And the idea is that the robot is in this free play phase where it can just do anything with this. We have a particular observation where we already see the object, so we are not having a vision problem here. And then we use a graph neural network as a forward model. So every object here is a node in the graph, and then of course we predict the dynamics, so then messages are passed in this GraphNet to predict the future. Then we take this and predict this n steps in the future action. So this is depicted in this part of the diagram, and we measure how much we are unsure about the prediction at the end. And so we plan for those paths where we have accumulatively the largest disagreement, and we maximize it. Okay. So it's the same objective actually in plan to explore. And now with the GraphNet and a few other tricks. And so now let's look at how this works. So here is a free play phase. At the first iteration, of course, the robot does nothing. And then we take this data and update the model. And then we do another iteration. The iteration is like 20 short episodes of trying something. Now let's look at how this really works. So first iteration, you have been really seeing, nothing really happens. After 8 iteration already, the robot starts to move an object around. And after 20, really interesting stuff happens. Objects are grasped, put over each other. And after 30, we see that that the behavior gets even more interesting. Two objects are grasped, things are thrown on top of each other. And so it's really, it's very interesting behavior that only comes from this very simple objective, namely to go to places where I have high epistemic uncertainty, so where the model really doesn't know yet. And you see that with increasing time, the behaviors get more crazy, and it's mostly then about throwing these dice, because this is really hard to predict, and it really tries to understand this better. Okay, so good so far. So far, so good. Now we can look at a few, statistics, what actually happened in this free play. And we can look, for instance, of how much an object was moved, which you see on the left. And you see two different types of methods that are based on planning. So our method is called CS, and the other baseline would be the same, but with the MLP. So not with the graph net, but the normal neural network. And you see that there is already a difference in this for two objects. And the baselines, they use policy-based optimization. So they would use rewards like this disagreement reward, but they would not use a planner, but they would use a policy. And in this allocated time here, these methods are not able to do anything on this task. They would just need much more. Then they would need an order of magnitude or 2 orders of magnitude more data. Okay, cool. And now let's look at a little bit the time scale I have talked about due to this iteration. So how long is that really? So 30 iterations is about 1 hour. And so this entire episode that we were, this entire training that we are running for 150 episodes is about 6 hours it corresponds to 6 hours of real world time. So that's not too bad. Comparison, let's say a method that was proposed by Groth et al. Also uses this curiosity, but they don't do this planning, and they need about 10 million iterations to get the first lifting, and we do this here after already an hour, so 60K transition, so huge performance gain. But now, well, maybe that's nice. We have seen a playing robot. Can we do something with it? And that really is the exciting part. We are now exchanging the cost function. Instead of maximizing ensemble disagreement, we are maximizing for a particular task reward, for instance, stacking, pick and place, throwing, and flipping. And the tasks are specified by us. So we just have specified a cost function or reward function, which would measure, for instance, here, minimize the distance between objects and their targets, or here you will see the distance between objects and where they're colored boxes. So here on the left, you see stacking, and on the right, you see throwing. I think both are really interesting. The throwing is quite cool at the moment. Just have a look at it. So the planner realized that it cannot move them there, so it has to throw them, because that's the only thing to get these ones. On the left, you see stacking, which is also quite interesting. Maybe you look at this one now. Of course, the robot is not perfect. It sometimes messes things up, but what's really cool is reactive. So now you see, for instance, the tower is falling off, and it immediately repairs it. I'm not sure how well this comes over Zoom though, but I hope you can see enough of it to see why I'm quite excited about it. So that's pretty nice. Another task would be, for instance, putting all objects in a particular place, or flipping objects so that the blue face is up. Yeah, this just works out of the box without any pre-training. Any further fine-tuning is zero-shot generalization to a new task. The only thing we have to do is specify the reward function. And here a little bit more quantitatively in numbers. So as we use a graph net, it doesn't matter how many objects are in the scene. So we are only training in the free play with 4 objects. And so the blue lines are what a normal MLP can do with the same kind of method. And then we do the same thing with the graph net. We see that we are able to pick and place perfectly with 6 objects. We can do stacks. Higher stacks are more complicated, but it still works. We can do throw quite nicely, flipping and all this kind of stuff. We have also been looking at now whether offline reinforcement would be an option to extract policies, such that we can run them very fast at runtime, but these methods are really quite the RL methods are not quite there yet. So this is a task for the very simple reach and pick and place. And you see, depending on how we collect the data, so whether we collect the data with our method or with other methods, this is a performance of offline RL method, CRR, in order to create this. And you see that CRS creates very good data, but still the performance on a very simple like pick and place for one object is not great. We had 99% or something on the task before. Okay, so I think there's lots of stuff to be done, and we have some interesting paper on this also, how to make offline RL work in these kind of domains, and we have figured out that there are some pathologies that happen with the value function learning, and so please check out that paper. Okay, so now a summary is we are able to use model-based planning with ensembles to go directly for epistemic uncertainty. That seems to be quite a good combination and really creates great sample efficiency, and maybe the first demonstration of a task agnostic free play to zero-shot generalization in a difficult setup like this fetch pick and place. Still lots of limitations, of course, but I think that's really interesting direction. So now, do I have a few more minutes or?
Yeah, we have 10 more minutes, 8 more minutes or so.
Okay, I think I'll be fine in 5 minutes or so max. So now this, we have seen this free play. I think it's an interesting thing, but also it's quite random what happens. And if we think about it, novelty is not necessarily any kind of usefulness. So that if the space is vast of things you can do, then just doing new things doesn't mean that it's actually anyhow useful for any task. So some have to specify a little bit of what kind of task family you want. And if we think about kids, then they would probably start to create certain kind of structures, recreate things they have seen in the real world, rather than just trying to figure out how the dynamics works. So we have clearly a generic bias for constructing things. And we thought that maybe if something relatively generic is to think about regularity as a driving force. So if we build something we are kind of torn towards creating structures which are regular. A certain kind of symmetry in them. And this, of course, in nature is very, very common. You have this in the animal and like in biology, in animals and plants, and of course, but also in the stuff that we create as humans. And so now the question is, how can we create this as a computable quantity? And we call this regularity as intrinsic reward. And how does that work? I'm making this relatively short here. Imagine you have a scene, let's say these objects, and you would like to measure the regularity of this. And we have been thinking about this for quite a while, and then we came up with sort of one framework in which you can express it. So we say, okay, first you all have to select a representation in which you want to consider regularity. For instance, here it could be the representation where you look at the relative positions or distances or vectors between these objects. Then you can take these vectors and put them into just collect them all and then put them into a histogram. Here, for instance, the vector 2020, which is a diagonal one, would appear a few times, or the one that goes left and right. Maybe you take the absolute values, then these two also collapse. So it depends on your parameterization, you will get such a histogram. And the more peak this histogram is, the lower the entropy of that histogram, the higher regularity, of course, right? If everything is in a single line, then you get lots of repeats of your positions, rather of these relative positions, rather than if they are just randomly. Okay, so in this case, color is not considered, but color could also be part of the representation. So our reward rare is simply the negative entropy of a particular description of the scene. So this histogram. Okay, now let's see what happens if you take here an example where the controller can move these little palettes around buttons, and now color plays a role. So it will create a structure which is somewhat regular, where both position and color are somehow nicely assembled. And depending on how you started, you will end up with some new different positions. So that's really quite nice. And now let's see what happens. And we do this in our page pick and place with a perfect model. So this is now here the place where we are creating, for instance, a stack. Something I forgot to mention, that our representation is only XY. So if stacking means all of them are exactly at the same position, and that's why it's really preferred. But you see that it was creating structures, lines, stacks, and other kind of regular things. Now we can put this together in our free play where we have this rare plus information gain together. So you see, still the thing is creating stuff, but also just likes to destroy it because that's the information gain part. And while it is creating stuff, it really tries to create stuff that is a little bit more structured. For instance, things, it moves cubes together in a line or builds small stacks and this kind of stuff. That's kind of biasing this otherwise completely agnostic free play for particular things. And of course, if we do now tasks which are more geared towards construction, we have a boost in performance as we expect. So for all these kind of things, we get a boost. And for things which are more chaotic, like throwing and flipping, we get a slight performance drop, but not actually a lot. But it's really also interesting, we can start to recreate structure. So if you have already a tower here, then the model would recreate the structure because it's the thing to minimize to maximize regularity is to do that. You see, so that's how the system would like to recreate things it has in the scene, just from this very simple objective. I think now it can't reach that. Anyway, very good. So maybe you were wondering, can we also do some more hierarchical stuff? And we have also a paper at IKEA this year where we take these systems and use hierarchical world models to be able to plan even longer and so on. With this, I would like to summarize and thank a lot for your attention. So I've been talking about intrinsic motivations because they help us to formalize exploration strategies and we are able to specify generic inductive biases that are helping a whole family of downstream tasks. I think model-based planning and predictive information gain is really promising. I hope we are close to having real robots play and also become useful then to particular tasks. We are looking at some hardware that we have in the lab and trying to make this all work. Also, we have this regularity as an addition to the zoo of already existing intrinsic motivations. With this, I would like to, of course, thank my team, present you my team, which is really fabulous and has done, of course, all this fascinating work, and my funding agencies, and of course, you for your attention.
Thank you very much for this great talk. Let's see if there are any questions.